Why are similar triangles crucial for structural analysis? Imagine trying to build a bridge or a tall tower without knowing how forces distribute or how to measure difficult parts. It sounds tricky, right? That's where similar triangles come into play. They are like the secret code that helps engineers understand and solve complex problems in building structures. When two triangles are similar, they have the same shape but not necessarily the same size. Their angles are equal, and their sides are proportional. This means if you know the size of some parts, you can figure out the rest by scaling. In structural analysis, creating scale models of buildings or bridges is common. Because similar triangles keep the same shape, measurements from these models can be scaled up to real structures accurately. This helps engineers test how strong or stable a design is before actual construction begins. For example, if a model shows a certain angle or length, the same ratio applies to the real structure. This saves time and money because it reduces guesswork. Triangles are naturally stable shapes, which makes them perfect for supporting structures. When a structure is divided into triangular sections, the forces acting on it are easier to analyze. Using similar triangles, engineers can understand how weight, wind, or earthquakes affect different parts of the structure. This helps in designing supports and reinforcements that keep everything steady and safe. Measuring heights or distances that are hard to reach is another benefit of similar triangles. For instance, if you want to find out how tall a building is without climbing it, you can measure the shadow it casts and use similar triangles to calculate the height. This indirect measurement is quick, simple, and very accurate when done correctly. Many structural elements like trusses, beams, and frames are made with triangular shapes because they are strong and resistant to deformation. Similar triangles help ensure these elements stay true to their design when scaled or under stress. This consistency is vital for safety and durability. In real-world applications, similar triangles are used in architecture to measure heights using shadows, in bridge construction to analyze load distribution, and in surveying to calculate distances between points. Their predictable proportional relationships make solving complex problems much easier. By understanding how similar triangles work, engineers can design safer, more efficient structures that stand the test of time.